There are many missile defense systems designed to stop incoming threats. Systems like the Patriot, THAAD, and Israel's Iron Dome are built around one core objective: detect, track, and destroy missiles in real time. But what actually determines whether they succeed or fail comes down to how these systems perform under real-world conditions. Because despite all of this advanced technology, missiles still get through. And to understand why that happens, we need to break down exactly how these systems operate, where their limits begin, and what happens when those limits are pushed. Let's first understand the basic concept behind missile defense. At its core, every system follows the same fundamental process. First, detection. Radars scan the sky constantly, searching for objects moving at extremely high speeds. Once a missile is detected, the system immediately shifts to tracking, calculating its speed, altitude, and trajectory in real time. Then comes interception, where defensive missiles are launched to collide with or detonate near the incoming threat. Finally, there's evaluation, where the system determines whether the target has actually been destroyed. This entire sequence happens in seconds, sometimes even fractions of a second, and depends heavily on speed, accuracy, and coordination working perfectly together. To give you a better sense of the scale and speed involved, consider a typical ballistic missile. After launch, it can reach speeds of over 24,000 kilometers per hour, which is roughly Mach 20. At that speed, a missile can cross an entire city in seconds. That means it's covering several kilometers every second, leaving almost no time to react. And at those speeds, even the smallest miscalculation in tracking, just a fraction of a degree, can result in a complete miss. This is where the first major challenge appears: reaction time. From the moment a missile is detected, the defense system has only a very limited window to respond. If detection is delayed by even a few seconds, the chances of a successful interception drop dramatically. Now let's compare a few different types of defense systems to understand how they handle these challenges. The Patriot system, for example, is designed primarily to intercept short to medium-range ballistic missiles and aircraft. It uses radar-guided interceptors that rely on continuous tracking updates. The THAAD system operates at much higher altitudes, targeting missiles during their terminal phase as they re-enter the atmosphere. Meanwhile, Israel's Iron Dome focuses on short-range threats like rockets, using a cost-effective interception strategy that prioritizes only those projectiles predicted to hit populated areas. Each of these systems is highly advanced, but each also operates under specific limitations based on range, speed, and coverage. To better understand how missiles still get through, let's break this down step by step. Step 1 is detection and tracking. Radar systems are incredibly powerful, but they are not omnipotent. They have limitations based on line of sight, curvature of the Earth, and environmental interference. Low-flying missiles, for instance, can remain hidden behind terrain or below radar horizons for a significant portion of their flight. This reduces the available reaction time and increases the likelihood of a successful strike. Step 2 involves saturation. This is one of the most effective ways to overwhelm a defense system. Instead of launching a single missile, attackers launch dozens, sometimes even hundreds, at the same time. Each defensive interceptor can only engage one target at a time, and even the most advanced systems have a limited number of interceptors ready for launch. When too many incoming threats appear simultaneously, the system is forced to prioritize, and that means some missiles will inevitably slip through. To put that into perspective, if a defense system has 50 interceptors available but faces 100 incoming missiles, even with perfect accuracy, at least half of those threats cannot be engaged. Step 3 is maneuverability and unpredictability. Modern missiles can perform small but critical adjustments during flight, especially in their final phase, making their path much harder to predict. Some even combine this with decoys or electronic interference, forcing defense systems to constantly recalculate. These rapid changes reduce interception accuracy and increase the chances of slipping through. In some cases, even slight zigzag movements at hypersonic speeds can throw off interception calculations, since defensive systems rely heavily on predicting a stable trajectory rather than reacting instantly to continuous changes. Step 4 is speed and trajectory complexity. Hypersonic missiles, which travel at speeds greater than Mach 5, introduce an entirely new level of difficulty. Unlike traditional ballistic missiles, which follow a predictable parabolic path, hypersonic weapons can glide through the atmosphere and change direction multiple times. This makes their trajectory far less predictable and significantly harder to intercept. At such extreme speeds, the margin for error becomes almost non-existent. Step 5 is system limitations and cost. Each interceptor missile can cost anywhere from tens of thousands to several $1,000,000, depending on the system. This creates a strategic imbalance where attackers can use cheaper offensive missiles to drain expensive defensive resources. Over time, this cost asymmetry can weaken even the most advanced defense networks. To better visualize how all of these factors combine, imagine a scenario where multiple missiles are launched simultaneously from different directions. Some fly high, others stay low to avoid radar detection. A few deploy decoys, while others maneuver unpredictably during flight. The defense system must detect all of them, track each one accurately, and launch interceptors in the correct sequence, all within a matter of seconds. Even with near-perfect efficiency, the complexity of this situation makes it almost inevitable that at least some missiles will get through. Another critical factor is geography. Terrain plays a significant role in how effective a defense system can be. Mountains, buildings, and even the curvature of the Earth can create blind spots where radar coverage is limited. Coastal regions, for example, may face threats from sea-skimming missiles that remain just above the water's surface, making them extremely difficult to detect until the last possible moment. There's also the issue of coordination. Modern defense systems often rely on multiple layers working together, such as long-range detection systems feeding data into short-range interception units. Any delay or disruption in communication between these layers can reduce overall effectiveness. In complex environments, even small coordination failures can have large consequences. Let's take a closer look at how interception actually works. Once a defensive missile is launched, it relies on continuous data updates from radar and tracking systems on the ground or from other platforms. These updates allow the interceptor to adjust its path mid-flight, correcting even the smallest deviations in the target's trajectory. In many modern systems, the interceptor doesn't carry a large explosive warhead. Instead, it uses what's known as a hit-to-kill approach, where the objective is direct collision with the incoming missile at extremely high speeds. To put that into perspective, both the interceptor and the target can be traveling at several times the speed of sound. This means the timing and positioning must be almost perfectly calculated. Even a slight delay in data transmission or a minor tracking error can cause the interceptor to miss by just a few meters. And at those speeds, that's more than enough for the target to continue its path uninterrupted. Finally, let's consider the real-world implications. Even if a defense system successfully intercepts a very high percentage of incoming missiles, the remaining few can still have a significant impact. In large-scale attacks, even a small number of successful strikes can damage critical infrastructure, disrupt operations, or create strategic pressure. This is why missile defense is not designed to be perfect, but to reduce the overall effectiveness of an attack. To better understand this, imagine a scenario where dozens of missiles are launched simultaneously toward a single region. Even with highly advanced systems in place, some targets may be prioritized over others based on predicted impact zones. This means that certain areas may remain vulnerable by design. At the same time, factors like limited interceptor availability, system fatigue, and the need for rapid decision-making under pressure all contribute to the outcome. These realities highlight an important point. Missile defense is not about eliminating every threat, but about managing risk in situations where absolute protection is simply not possible. So while modern air defense systems are incredibly advanced and capable of stopping many incoming threats, they are not invincible. Limitations in detection, reaction time, system capacity, and cost all contribute to the reality that some missiles will always find a way through. And as technology continues to evolve on both sides, the gap between offense and defense remains one of the most complex challenges in modern warfare.